roll the gravel downstream like that than it is to turn it around and go like that. It takes more force to roll up gravel like that, end to end, than like that. Just imagine you're at the family picnic. Nice day, and Granny slips into the stream. And it's a turbulent stream. Which way is Granny going to go? Downstream?
To the bottom of the roll.
You would hope that Granny would roll over via, you know, her middle, her waist, rather than go head, foot, because Granny will bash her head the whole time, won't she? Okay? So, same with these gravels. They tend to roll like that, and you get it. You can tell which way the flow goes based upon the orientation of those gravels. Now, if this all got filled up with sediment, and it really just comes through then, doesn't it?
Yeah.
And fills up with sediment, and the stream moves over there, and you became a sedimentary geologist, and you came through. You could find these gravels. You could say, oh, well, I know which way the flow was in this stream based upon these. And often these gravels will do this. Well, it's not doing it so much here, but they'll pile up against each other. They'll sort of pile up like this, like that, and like this. Yeah, like that. See how they're sort of ballooning against each other like that? We call that imbrication. It's like tiles. You know, if you get dominoes and you line them all up on their short axis standing up, you know how people tap them and they all fall down? You know how they lie against each other? That's called imbrication. So then you can get a direction of flow. You know precisely that it was going this way, not that way. So we've got these gravels. They're of a certain size. They're in the main part of the channel here. We don't tend to find as many gravels up there. They're in this main part here where the main part of the flow goes. There'll be a greater discharge here. There'll be a greater velocity here than there will be probably just up there. So the coarser clasts are going to be transported by the higher velocity part of the flow. Does that make sense? So the size of these gravels can give us an indication about how fast this stream flows. Notice that we don't have like gravels that are the size of small cars. You just got hit by it then, didn't you? Stand, if you want, if it's really affecting you, just stand off the bank a bit. And well, let's walk up there. Put down a bit. Just in this shady area here would be good. So once again, see the gravels? And as I said, the size of the gravels is not the size of a small car. Okay, there's a limited size to these gravels, and that gives us some indication of the velocity of the flow and the discharge that comes down here. So the bigger the discharge, the bigger the gravels that this stream could transport. So there will be a limit to the size of the material that can be transported down here. So we can actually, we've got equations that we can use. We measure these gravels, and we can work out from those equations how fast the flow needs to be and what the discharge is likely to be. Another thing that sedimentary geologists can get out of their sections, and they can work out how big the river was, etc. Does that make sense? You go down Barron Gorge, go down into the gorge halfway from sort of Lake Placid up to the power station, walk down there, you see the size of the boulders down in there that have been transported down the river. They're 4 and 5 metres across. Again, indicative of the discharge and the size of the flow. Now, we're not going to get boulders 4 and 5 metres across here because this stream is too small, the catchment is too small, we're just not going to get enough water into it in a rainstorm. But the Barron River catchment, of course, goes from Mount Halkipani, etc. You know, it's a bigger catchment.
So, just a quick one. For example, how do you know what has been eroded away and what has been moved down? What tells you what's the difference between a boulder that's been moved as opposed to eroded from?
Okay, the key thing we look at is its depositional setting. If it's oriented with its long axis perpendicular to the flow, and it's imbricated, we know that that has been transported by water.
Yep.
As opposed to just when boulders just roll down and fall in, they won't land that way. So this is a depositional or transportational fingerprint that we can use.
Yep.
So that's how we would do it.
This is all cut into alluvial plain as well, though.
It is. This is cut into it. This is all part of the alluvial fan. Okay.
So there isn't any native parent material here from this area?
No, it's not cut into bedrock.
It's all from up there somewhere.
This rock's out of up in the hills.
I was saying, what you're saying with the big rock of the gorge. So those implications that you're suggesting would tell you they've been put there as opposed to eroded away and...
That's right, yes, that's exactly right, yes. The force required to overturn, to initiate movement, to just lift it up and overturn it, is greater than the force required to keep it in motion. So the force that's required to initiate movement is greater than to initiate, to continue to transport it. So that getting over that inertia.
Once it's moving,
and that requires a certain velocity flow. So as part of this prac, not today, but this series of pracs, we're going to come in here and measure these. And you're going to measure them using 3 axes. The A-axis is the long axis. The B-axis is the intermediate axis, and the C-axis is the small axis. A, B, and C. And we get a general measure. And I think each group's going to measure 20 of these. From that, we are then going to use some equations to work out what these gravels tell us about the flow of water coming down here.
Do you measure them in like zones?
Yeah, we'll get you to break up into groups, and some people go up there, some people come down here, etc., etc. So obviously if you go and measure those ones up there, there's a few bigger ones up there. The idea is to measure the biggest ones, rather than just have a random distribution, as you might do if you were sampling for ladybirds, lady beetles, or plants that you might do in biology, because you want to understand the variability in the population in that situation. We're not really interested in the variability in the population here, because the bigger the boulder, there's a threshold. Anything that can move this can also move this or this. So this isn't giving us that much information. We want to know the biggest stuff that's down here. So we're looking at a threshold. Does that make sense?
Would you then take several different places to get a more... Because if you just took it from one side...
You would. Yeah. That's exactly right. You would. So we're interested in the biggest ones, not the distribution of sizes.
But presumably you'd have more energy back up there and you get bigger stuff.
That's right. That's exactly right. So the class size tends to be bigger further upstream, and it gradually gets smaller as you go downstream. Okay. So we once had an honour student do a project where she went in and measured boulders like this, and she took the biggest boulders. And that thesis was marked by me, and also by a professor of biology who was our head of school at the time. It was a different school at the time than it is now. And that professor at the time said, no, she marked this young lady down because she didn't do a proper sampling program. And she said, well, you've just selectively picked out the bigger ones. That's not how you go and sample. How do you understand about the variability in the population? We had a heck of a time trying to convince her that that's not how we do things in the earth sciences. And for these reasons, she still didn't get it. Just didn't get it. But that's horses for courses. Does that make sense? So this is how we would sample it for a very specific reason in that regard. So sediment size does decrease as you go downstream. Okay, we'll get out of this zone after a while, and there'll be no gravels left. You'll be just into sand-sized materials, etc. Does that make sense? But it gives us an indication of what's going on. About that. Either bank, down there or down there.
It's like a compressed clay with small rock gravel inside it.
Yep.
Hematite? Yeah.
Mottled? It's mottled. Exactly. Now mottling can sometimes be a surrogate for age. And it'll give us a bit of an indication of age. Now I'm not sure whether this material is sediment that's been brought downstream and then indurated subsequently, or whether it's some of the basal part of the fan. I'm not too sure. But the key point is that we've got our gravels here. We've got this indurated, hard.
Didn't say what does induration mean?
Induration means hard. It's like when sand turns to sandstone, or it's in the process of becoming sandstone, it's indurating, becoming hard. It's indurating because it's weathering, and the iron oxides and this chemical weathering going on, and you've done all this in yourself, haven't you? Talked about ferruginous soils and stuff like that. So it's indurating and it's mottled, which suggests that it's of some age. But if you look on the banks above this, is that the same material?
No, it's
This.
There's got a bit more organic material going on.
Yeah. And we can see it here. Here's this harder, indurated, mottled material. It's a sediment. It's not bedrock. It's a sediment. But above here, this stuff is much softer. Look. And it's not mottled. So we've got 2 units of sediment. We've got this stuff overlain by this younger material. You can see it's a browny colour. Probably a snake up in there. You can see it there. It's not. See that? It's not mottled. It's quite crumbly. I mean, you guys are now soil scientists, so you can tell me all about the structure of this, and you should be able to make it into little donuts and tell me its texture. You do that?
We have done that.
Yeah. So you know all about it. Okay. So you could describe it, but it's clearly different to that stuff down there, isn't it? So this stuff, the law of superposition in geology tells us that this stuff has to be younger than this stuff. Yeah? Boy, would it be weird if it was the other way around, wouldn't it?
Magic.
But it is. This stuff is younger. So this is more recent deposit, and that's what's making up this area of floodplain, or that whatever that is, a bench cut into it.
Probably also suggests that the water level would have to get up pretty high before it starts actually eroding away.
That's right. This stuff here is quite resistant to erosion because it's quite hard, but up on top of that, this stuff is much easier and more readily eroded. Now these tree roots are becoming more and more exposed, so this has actually been cutting back progressively over the last few years.
So will it cut back and make a new floodplain, like a lower?
Well, the banks will chop back. It'll chop back like that. Remember also that some streams, many streams, shift. They shift laterally. So they'll erode on one side and actually deposit sediment on the other side. So the channel migrates across its floodplain. And it can move backwards and forwards over many thousands of years. It can migrate laterally. Does that make sense? So if this channel migrated that way, it would start depositing sediment here. This would all be filled in, and the channel would be over there. Yeah?
This looks like it's actually cutting that way, isn't it?
Yeah. Yeah. Some streams can stay fairly stable and don't migrate that much laterally, but it's common for streams to do that.
Just with what you just said, doesn't matter too much if it's like an intermittent stream or a perennial kind of stream, or
how do you mean?
Like with the deposition, and obviously like perennial streams would take probably longer to erode away. It's kind of
the thing about it is that most of the work is done in a short amount of time.
Yeah.
So it's the big events that the work gets done in. So you just got normal flow of water coming down here. Not a lot of work's going on. It's those big events that do the work. So it's a disproportionate amount of geological work is done in a very small number of flows. It's those big flows that do a lot of the work. And of course the work that the stream does, apart from its ecological functioning, which of course is critical too, but it has geological work, and that is to transport sediment from up there down into the sedimentary basin, being the sea, the ocean basin out there. So it has geological work to do. And that's another concept and term that I'm going to be talking to you about. You know, how much energy is available to be able to do this sort of work? Actually, Chris will probably talk to you a bit about this, but I can go over bits and pieces of it in mini lecture. So that's what we've got here. Take note of how high the banks are. They're fairly steep. You can see here that there's a unit of gravels at the base of this. See these gravels in here? You can almost see some of these gravels look a bit imbricated, those bigger ones just over there. So at one point that would have been the equivalent of this area here. The channel bed would have been at that level. And then we would have had the finer grained sediment put above it. So the coarser material is transported where the flow is faster. As you get up higher, the flow doesn't necessarily